All right, good morning again, guys. Today we'll continue our discussion about power series or the basics of power series. I think last time we went over this and said that power series has either of these two forms. The first one is an expansion around x equals 0, and this guy's an expansion around x equals a. But the main point here is to find the interval of convergence or the radius of convergence for the following series. And I guess we have two methods on how to do that. First, you can check if the power series is geometric in form because that's easier. Because when the coefficients of your powers of x are just const or is just a constant, then it's a power series, and you can just take the absolute value of x, compare it to 1, and that would be your interval of convergence. But in a more general case, we need to apply either the ratio or the root test. We check for x values for the limit of where the corresponding limit is less than 1, and thus they belong to the IOC. But when L is equal to 1, then the ratio and the root test are inconclusive, so we need to do another test. Specifically, we need to plug in those x's at the endpoints of our interval to see whether the resulting series will converge or diverge. I guess last time we considered several examples. Let me just add one more here before I go to before I check the chat. Okay, so again, just to recall what we did last time, let's do problem 5, and we want to see the interval of convergence of this series, x minus 6 to the power n all over n to the n, and going from 1 to positive infinity. And here we see we have n to the power n, so it seems that the root test would be more applicable here. So maybe I'll use the root test because the n's there are n's in the numerator in the exponent, so I guess the root test is much more convenient for this type of series. So we'll take the limit of our an and raise it to 1 over n as n approaches infinity, right? But that will just be exactly x minus 6 to the power n all over n to the power n all raised to 1 over n. The reason why the root test is specifically suitable for powers involving the variable n is due to the loss of exponents, because here we can write it as x minus 6 to the power n raised to the 1 over n, but remember, raising a power to another power is just multiplication of the exponents, all over n to the power n times 1 over n as n approaches infinity. And when we simplify, we'll just get the limit, or actually I forgot the absolute value bars here, because we're checking for absolute convergence of this power series. So they must be enclosed in absolute value bars. So here we see that in the exponents, the n's will be gone. So we'll be left with absolute value of x minus 6 all over n as n approaches infinity, right? I can free the n out of the absolute value bars because n is always positive, right? Meanwhile, I don't know what happens to x minus 6 because x can take any value, so I'll just leave it inside absolute value bars. But the thing is, the numerator is free of the limiting variables. So we are taking the limit as n approaches infinity, and the numerator doesn't involve the variable n, so it can come out of the limit because you can treat it as a constant, and we'll just be left with this as n approaches infinity, right? But what is the limit of 1 over n as n approaches infinity? This guy will go to 0 because n becomes very, very large, right? So this will just be absolute value of x minus 6 times an exact 0. When you're multiplying any number, like absolute value of x minus 6 by 0, you will get 0 as well, all right? And obviously, this is less than 1 for any x. Since the limit of the root is less than 1 for any x, then here the radius of convergence, or sorry, the interval of convergence is from minus infinity to positive infinity. because we see here that the series will converge absolutely for any value of x, because no matter what x is, the limit of the nth root will just go to 0, which is less than 1, right? So you can also write this interval as simply the set of real numbers. All right. Let me see. Okay, so let me see Morel's question over here. You need to check whether this is converges absolutely or converges conditionally. So I guess for this one, let me see. Hersen is a suggestion here. Yeah, so for this particular problem, I will try the alternating series test, because you see here that the limit of the positive part is 0 because the denominator has a higher degree than the numerator. But is it decreasing? I guess you can show that this is decreasing because the denominator is degree 6. The numerator is degree 5, so the denominator will grow a lot faster in the long run. So yeah, though you need to show yeah, you need to show that it is decreasing, and with that, I'll go with John's suggestion, that is to take the derivative and see that this is always negative. Though evaluating the derivative will require some more work, because you have a degree 5 over a degree 6. So the derivative will be complicated. You're going to use the quotient rule, but nevertheless, you'll be able to show that that is less than 0. Okay. Yeah, because I tried using the ratio a sub n plus 1 all over a sub n and compared it with 1, and also the difference a sub n plus 1 minus a sub n, and it's not that easy to see that that is negative, right? So that's why my go-to thing is to look at the derivative and observe its sign, and not bother with other details. Okay. Let me see the other questions here. I'll defer your first question, John, later when we start talking about the Taylor series expansion, as well as your second question. So yeah, let me just finish this up, which is the basis for using power series without going into the derivatives. So the main point here, or actually the tool that we can use now, is the geometric series form. So for differentiation and integration of power series, okay. So we will start with this from a result from the geometric series. Remember that if you have sum of ar to the power n going from 0 to positive infinity, we said that this is equal to a over 1 minus r whenever the absolute value of r is less than 1, right? So we can use this result for geometric series to come up with a series expansion for functions of this form. So imagine if I replace a by 1, so I'll take a to be equal to 1 and r to be equal to a variable x with the absolute value of x less than 1. So we know then that 1 over 1 minus x has the series expansion x to the power n going from 0 to positive infinity, right? So this usually serves as the basis for the power series that we can derive as of the moment, disregarding the fact that you already know how to use Taylor and Maclaurin series. But basically, this is the foundation using geometric series. Now, from here, I can also replace. I can also take. I can replace x by any other expression as long as it has magnitude less than 1. So for instance, we can use this statement to find a series expansion for the following. So find a series expansion for the following. Okay, let's start with number 1, 1 over 1 plus x. Well, here it's 1 over 1 plus x, which is very similar to this guy, except that I need to rewrite it as 1 over 1 minus negative x. And comparing this current form to this one, it seems that I can use the same expansion, except that I need to replace all x's I see by negative x. So basically here, this would be the sum from 0 to positive infinity of what? Instead of an x, I see here that the common ratio is the absolute value of x. So that means I'll have a negative x raised to the power n. Or you can rewrite it as negative 1 to the power n, x to the power n, as n goes from 0 to positive infinity. And this is one series expansion for this expression. All right. Yeah, let me just go to Herson's post in the chat. He said, I tested something the other day and it seems like the degrees do show if it is increasing or decreasing. If the power of the numerator's degree is bigger than the one in the denominator, it seems to increase. If the denominator degree is bigger than the one in the numerator, it seems to decrease. Your observation, Herson, is correct. If the degree of the numerator is larger than the degree of the denominator, then the series will eventually increase. If the degree of the denominator is larger than that of the numerator, then the terms in the series will eventually decrease. And the keyword there is eventually. So for large n's, you will see that behavior. But for smaller values of n, it is not clear whether it would increase or decrease. And that's why I am very hesitant to use that simple argument in the alternating series test, because I'm not sure how the alternating series test was specifically phrased in the lecture. Hold on, settle this once and for all. Let me see the textbook, because I guess the usual statement of the alternating series test is that the terms should be decreasing. So that means it should be decreasing for all values of n or all values of k. But the more general version of the alternating series test only requires the terms to be eventually decreasing. And so if the statement of the AST in the lecture is that the terms will eventually decrease, then your method would be acceptable. So let me see. Yeah, I'm looking now at the textbook, and it says the alternating series test was phrased this way. If a sub k is a decreasing sequence of positive numbers, and if the limit of ak as k approaches infinity is equal to 0, then the alternating series is convergent. The statement required that ak is a decreasing sequence. So, and that's a very strong requirement, because if you say that ak is decreasing, that means a sub k plus 1 should be less than a sub k for all k's. And if I see at least one value for k that this statement doesn't hold true, which is possible for polynomials over polynomials, even if the denominator has a larger degree, then I am violating the premise of your version of the alternating series test. But the more general statement of the alternating series test is not this strict. Some versions just require that a sub k is eventually decreasing. And if that's the case, then your observation horizon is acceptable. And I guess that's one main contention why I think I was hesitant to accept that simple solution, I guess, in the last lab or the last before our last meeting. But yeah. But this is valid. So I guess you can clarify that with Dr. Almas and just ask her if you will be allowed to do that argument, because I think that's much easier. Because you're correct. If the degree of the denominator is larger, then it will eventually decrease. So if I'll be using the more general statement of the ASC, then that is sufficient. But if I'll use your textbook version, then that will not suffice because I should be able to show that it is decreasing all throughout, all right? But that's a good point. Kindly ask her. And then, yeah, if she allows you, then be mindful when you get your FRQs because some TAs might not be familiar that, okay, I see. Because, for instance, I as a TA will look for a detailed explanation why it is decreasing. So I expect to see derivatives and so on. But if Dr. Almos will allow you to do that, then we should comply. So if you see in your FRQs that some points were deducted out of the lack of a detailed solution, then just let me know and I can rectify those. All right. Okay. All right, so going back here, so that's our basic way of using power series, just adhering to the form and try to see how can we rewrite it so that it will be of the form a over 1 minus x, all right? And this expansion, by the way, is only true when the absolute value of negative x is less than 1, because our common ratio here is negative x, all right? Now let's play a little bit more with this guy. Let's see, let's try to expand 1 over 1 minus x squared. Nothing different here. So here our a is equal to 1 and our common ratio is x squared. Because remember the form is a over 1 minus r. So if you compare this guy with this guy, you see that a is equal to 1 and r, which comes after the negative sign, is x squared. So basically its series expansion will just be a, which is 1. So instead of an a, I'll just write 1, but it's a multiplication by 1, so I can ignore that. And then our common ratio is x squared, so I'll have x squared to the power n, and going from 0 to infinity. So this would be sum of x to the power 2n as n goes from 0 to infinity. All right, that's simple. Now, what if I have something like this? X over 2 minus x squared. Now, there are several ways on how to do this. One way is here I can rewrite it as x over 1 minus, what should be the thing here? I have a 1 minus, I should have a minus 1 plus x squared, right? So because I should adhere to the form a over 1 minus r, so I should always have a 1 followed by a minus sign. So I have a 1 followed by a minus sign, but in order to get back 2 minus x squared, I should have this group after the negative sign. So I have negative 1 plus x squared. When simplified, that guy will go back to 2 minus x squared. So here we see that our a is equal to x. So here, a is equal to x, and r, the common ratio, is x squared minus 1. So one series expansion for this guy would be the series of a times common ratio x squared minus 1 to the power n, and going from 0 to positive infinity. So this guy is a little bit unconventional because we have still here a power of n. Sorry, a power of x rather than simply x to the power x to the power n. What would be a nice way to deal with that? Okay. Another way to do this is what? I think I can do integration here, but I will have a minus still. So probably I leave it this way. And let's look at one more example, a more conventional example. Say I have 2 over 1 minus x quantity squared. So here we note that how can I write it, or how can I relate this to something involving a over 1 minus x? But I have a quantity squared here. So here we can note that, well, so if I have 1 over 1 minus x, that's what we want to begin with. And if you take its derivative, right, what do we get? So this guy looks like 1 minus x to the power negative 1, right? And if I differentiate this, I'll get negative 1 minus x to the power negative 2 times negative 1 by the chain rule, right? So this simplifies to 1 over 1 minus x quantity squared, which is a lot similar to what we have here, right? Except that you need to multiply it by 2. So in order to get 2 over 1 minus x squared, right? That is 2 times 1 over 1 minus x quantity squared. But we knew that this guy, 1 over 1 minus x quantity squared, is the derivative of 1 over 1 minus x. Derivative of 1 over 1 minus x. And I needed this relation in order to manipulate the series expansion for this guy. In particular, I can take its derivative to get the series expansion for the original function, right? So what I'm trying to say is, okay, I have a 2. I'll take advantage of the fact that I know that series expansion for this guy. So instead of differentiating that, I can differentiate the series expansion, which is x to the power n going from 0 to positive infinity, right? And this expansion is true whenever the absolute value of x is less than 1. If the absolute value of x is less than 1, then I know that this series is absolutely convergent. And the nice thing about absolute convergence is that you can interchange the order of the integral and the derivative. So instead of differentiating an infinite series, you can take the infinite series consisting of a bunch of derivatives. And that's the beauty of absolutely convergent series. You can interchange derivatives and sums, as well as integrals and derivatives. So this is not hard to do. You just have a 2. Then we differentiate all the things inside the summation. Now, what's the derivative of x to the power n? Remember, n is a constant, so you just need to use the power rule. The derivative would just be n times x to the power n minus 1. All right. And then you can just put the 2 inside the sum by the distributive property. So this is just the sum from 0 to infinity to n x to the power n minus 1. And this is valid for x's whose magnitude is less than 1. All right, is that good? Yes, Maria. Morel is right. You can do the same thing for 20 over 1 plus 20x, right? You'll just start with a series expansion for 1 plus 20x, or yeah, take note that that would be the derivative of some other function, but the process is similar. Okay. Now let's see, what else can we try? Maybe we can try this. Let's try problem 4. Yeah, give it a shot, Maria, and let me know if you have if you encounter some difficulties with that. But the process is the same. You just need to find a relationship between, actually, problem 10 is much easier because it's just a basic power series, right? You compare 20 over 1 plus 20x to a over 1 minus r. So you just need to rewrite it as 20 over 1 minus negative 20x. So here your a is 20 and your r is negative 20x. What's the second part to that problem? I guess the follow-up question will require you to take the derivative or the integral, whichever is the case. Because once you get an expansion for 20 over 1 plus 20x, then you can use it to express, you can integrate it or differentiate it to get an expansion for your function. And actually, what I'll try, my next example is supposed to be similar to part B of that question, incidentally. So I'm thinking, should I go with my example or go with that one? Perhaps I can go with my example so you can try it on your own. Yeah. I'll do ln of, an expansion for ln of 1 plus x. And you can do the similar thing to part B of question 10. So you can try it out. So here, I need to find the relationship between ln of 1 plus x and either 1 plus x, which we know the expansion of, or 1 over 1 minus x, right? But here I note that how do we get an ln's? So I want to find its relation to 1 over 1 plus x. Because so far, that's the only, this is the series that, this is the only series that we know the expansion of, or this is the only function that we know a power series expansion of. Yeah, exactly, Herson. So here you note that the integral, so here you have a rational function, and here you have an ln. So it brings to mind that when I integrate this guy, I'm going to get the given function. So that's what I'm trying to note here. Note that the integral of 1 over 1 plus x dx can be obtained by letting u equals 1 plus x. Du will just be dx. So this guy will be the same as du over u, which is ln of the absolute value of u plus c. So this will just be ln of x plus 1 plus c, right? So that means, we know the series expansion for this guy, at least for x's whose magnitude is less than 1. So I can integrate that series in order to get an expansion for the ln of 1 plus x, right? But note that that expansion, that's redundant. Maybe I'll just use also. We know that 1 plus x can be expanded as the series of negative 1 to the power n, x to the n, and going from 0 to positive infinity. This is what we got basically earlier. And this is true for all x's whose magnitude is less than 1. And since here x's magnitude less than 1, that means the absolute value of x plus 1 would be positive, right? So that means this perfectly fits our context. So let's summarize what we know. We found out that the ln of 1 plus x is the integral of 1 over 1 plus x dx, right? But we know the series expansion of 1 plus x, so we can write 1 over 1 plus x as the sum of negative 1 to the power n, x to the n, and going from 0 to infinity times dx. And again, this is true for all x's less than 1, right? Again, as long as the magnitude of x's are less than 1, then this guy is absolutely convergent. And absolute convergence allows us to interchange the order of the integral and the sum. So instead of integrating a sum, we can sum up the integrals. Right? And this is easier to do because now I can what? I can integrate this easily, right? -1 to the power n is a constant with respect to x, so it will come out of the integral. Times what's the integral of x to the power n? It's just x to the power n plus 1 all over n plus 1, all right? And so that's the series expansion for for ln of 1 plus x. And I guess this is one of those formulas that you can remember. When we go to Taylor series expansions, this might be helpful. The Taylor series expansion of ln 1 plus x is this guy. All right, all good so far? If the x is like x minus 1, we still do the same thing and we don't mess with the inside part. Yeah, that's, oh, by the way, where do you mean the x minus 1 will be? Will that be thing inside the ln? Or will that be the one inside the integral? Are you saying here instead of x to the power, we have x minus 1 to the power n? Oh, yeah. So the integral will simply be n times x minus 1, sorry, integral. So we have x to the power n, x minus 1 to the power n plus 1 all over n plus 1. But of course, you need to do the u substitution for the integral. So you will simply integrate it the usual manner. So u substitution let u to be equal to x minus 1, but du will just be dx, so it would be perfectly fine. Okay. All right, let's try another one. Maybe the last one for this topic, unless you have some questions on this. Let's try tangent inverse of negative x. All right. Or this is the same as arctan of x, right? So have you wondered how calculators can compute arctans, sines, cosines, those transcendental functions? Because all we know is that calculators can only do the basic arithmetic. It can only do addition, subtraction, multiplication, division, and exponentiation. But they are not designed to do transcendental functions like arctans, sines, cosines, and so on. Because actually, way back in the day, mathematicians make a living by selling tables of values for transcendental functions. So there are famous mathematicians who gain fame by selling books that only contains values for sines, cosines, natural logs, and so on. So that's how they compute it back in the day. But how do we implement it nowadays? We use actually series expansions. Because for instance, when evaluating ln of 1 plus x, normal calculators cannot do the computations of a transcendental function. So what instead, the mechanism inside the calculator will do a series expansion up to some degree. So they will just take the sum, say, for the first 10 terms of this guy, and that would be the approximate that it will give us for the transcendental functions. And that's the same thing for sines and cosines, which we will see later. So they are not really calculating the transcendental functions, but they're computing a truncated series, which is a good approximation for these transcendental functions. So let's try this problem. Thankfully, we don't have to buy those table of values for these transcendental functions. So arctan of x. Now, how can we relate arctan of x to the basic forms of functions that we have earlier? Well, you can recall that arctan of x is actually the integral of 1 over 1 plus x squared dx. Agree? Right, so this is our basic integration formula. And we also knew from above that the sum, that 1 over 1 plus x squared can be rewritten as 1 over 1 minus negative x squared, right? And so its series expansion would be sum from 0 to infinity of a is 1, and then the common ratio is negative x squared. Whenever the absolute value of negative x squared is less than 1, right? Actually, you can say whenever x squared is less than 1, that's fine. You can rewrite this as negative 1 to the power n, x to the 2n, and going from 0 to infinity, right? And this statement here tells us to get an expansion for arctan, we only need to integrate the series expansion for 1 over 1 plus x squared, which we already have here. So, we'll have arctan of x is equal to the integral. Instead of 1 over 1 plus x squared, I'm going to use its series expansion from 0 to infinity. And this guy is multiplied by dx. And this is true whenever x squared is less than 1. And whenever x squared is less than 1, the series is absolutely convergent. And the beauty of absolute convergence, we can interchange the integral and the summation. So instead of integrating a sum, we can sum up integrals, which is much easier to do, right? Because we just have a polynomial here. Then again, note that we are integrating with respect to x, so everything that doesn't involve the variable x will come out of the integral. Specifically, this guy doesn't have an x, so it can right away go out of the integral. And so we'll be left with integrating x to the power 2n. 2n is a constant with respect to x, so this is just an application of the power rule. So we'll have x to the power 2n plus 1 all over 2n plus 1. Oh, I forgot the arbitrary constant c after the integration. Likewise here, I forgot the plus c, which will require an additional step. Hold on. Let me just put this down so that we have step, right? I forgot to do this last step for problem 5, but let's do it for problem 6 for now. Let me see if that would be easy. Now, okay. All right. So now to find a value of c, you can choose any value of x in the interval of convergence. The usual choice is x equals 0, so that this entire thing will just go to 0. That what is arctan of 0? Arctan of 0 is the angle when tangent is equal to 0. It will be 0 when the sine is 0, and sine is 0 when the angle is 0, right? So this is equal to 0. So that means arctan of 0 is equal to the sum of negative 1 to the power n, 0 to the 2n plus 1, all over 2n plus 1, and going from 0 to infinity, plus the arbitrary constant c, right? And as we have noted, arctan of 0 is equal to 0, so this guy will be equal to 0. Okay? Now, this tells us that, oh, what is this sum? Can you tell me what this sum is? This is just a bunch of zeros added together, and it doesn't matter if there are infinitely many exact zeros, they will sum up to 0, right? So this guy will be just 0 plus c, which is c. So that means c must be equal to arctan of 0, but arctan of 0 is 0, right? So this means that, c is equal to 0. So our expansion for arctan we'll just have c equals 0, so we'll have this guy. Right? I was lucky because c turns out to be 0, so even if I forgot to put the plus c above, then I should have been fine. Okay? Now let's see, I forgot that step for problem 5, right? So, but here I can also plug in 0. And this is, I always choose x to be equal to 0 so that this guy will just be 0 to the power n plus 1. So you'll be adding up a bunch of zeros and they will just simplify to 0. But here, luckily, when x is 0, we'll have ln of 1 plus x, which is ln of 1, which is 0. And we said this should be equal to sum of -1 to the power n, x, which in this case is 0, to the power n plus 1 all over n plus 1 plus c, and going from 0 to infinity, right? But this guy simplifies to 0 plus c, so that means c must be equal to 0. So that means the actual expansion for ln of 1 plus x will be this guy, because c turns out to be equal to 0. All right. Any questions with this one? Okay, none. Unfortunately, I only have 3 minutes left. So let me go over to John's question quickly. Oops. All right. And then we'll revisit Taylor series expansion again next time. So for John's question, he's looking for the expansion P2n of x centered at 0 for f of x equals hyperbolic cosine of 6x. All right. Now, the Taylor series expansion has this formula. P sub 2n of x will just be the sum from k going from 0 until 2n, right? F upper k evaluated at the center of expansion. The center of expansion here is 0 all over k factorial x minus 0 raised to the power k, right? So this is the general formula for the 2n Taylor polynomial. You're looking for p sub 2n, so your summation will go until 2n. So first things first here, this is fine. You'll have x to the power k. K factorial will remain there. The challenge is expanding this, f upper k of 0. This just means the kth derivative of f evaluated at 0. So to find that, I'll start with f of x, which is cos 6x, right? But this is actually f upper 0 evaluated at 0. So you'll have cos of 0. But what is cos of 0? Cos of 0 is 1, right? And then we'll take a look at the pattern. What happens for the first derivative? The first derivative would be 6 hyperbolic sine of 6x. So that means f upper 1 evaluated at 0 will be 6 times sinh of 0. But sinh of 0 is equal to 0. So this guy will be 6 times 0, which is 0, right? You can move on to the second derivative. Just to see the pattern, the derivative would be 6 squared hyperbolic cosine of 6x. Remember, I'm applying the chain rule here. So the second derivative evaluated at 0 will be 6 squared times cos 0, which will become 6 squared. All right. The third derivative would be 6 cubed hyperbolic sine of 6x. So the third derivative would just be 6 cubed times sinh of 0, which will become 0. And I hope here that the pattern will be obvious, because if you have f upper 2k plus 1, which is an odd number, right? 2k plus 1 is an odd number, but you see that the first derivative is 0, third derivative is 0. if you go to the fifth derivative, you also see that this will be 0 because they will just alternate, right? 1, 0, 6 squared, 0. This will be followed by 6 to the 4th, then followed by 0, 6 to the 6th, and then 0, and so on, right? So the odd derivatives evaluated at 0 will be 0, while the even derivatives will be what? The 0th derivative is 1, which is the same as 6 to the 0. The second derivative is 6 squared. Imagine what will happen for the fourth derivative. The fourth derivative will be 6 to the 4th, and so on. So I know that the 2k derivative will be 6 to the power 2k. All right. So that means the sum will look like this. So p sub 2n of x will look like 6 to the 0 plus 0 plus, there's a 0 factorial here, x to the 0 plus 0 over 1 factorial x to the 1 plus 6 squared over 2 factorial x squared plus 0 over 3 factorial x cubed, and so on, right? Or in summation notation, here we see that all the odd values will be gone, right? All the odd powers will be gone. So I can just do the summation from 0 to positive infinity of 6 to the power k, 6 to the power 2k instead, right? Because if k is 0, I'll have 6 to the 0, which is that guy. That's fine. When k is 1, I'll have 6 squared, which is that guy. That's good. All over 2k factorial, because whatever the exponent was, they also served as the denominator factorial. Then x raised to the, what would be the exponent? If I have 6 to the 0, I'll have x to the 0. If I'll have 6 squared, I will have x to the power 2. So if I have 2k, then I will have x to the power 2k. And you observe here that everything will have an even exponent, because all those that have an odd exponent will just be multiplied with 0. So I guess this would be your answer here. All right. Is that good? Who asked the question again? Yeah, I hope that's okay, John. Let's see. Yeah, I hope that made sense. We'll do the same thing. Yeah, we'll revisit similar examples to this when we go to the formal Taylor series expansion derivations tomorrow. Sorry, on Friday. Yeah, exactly. Yeah, Herson. You need to go through the definition of the Taylor polynomial, and the Taylor polynomial requires you to find a pattern for the derivatives evaluated at the number. And I think that's the hardest part for questions like this. All right. So don't worry. On Wednesday. Sorry, I already lost track of the days now. So on Friday we'll talk about Taylor series expansion more. And yeah, that's why I would have used this as an example towards the end of the discussion, because the weird part really here, as Herson suggested, is the sub 2n. They just used the sub 2n because they knew that the odd exponents or the odd coefficients will all be 0. So that means everything will be gone except for those that will have an even power. And that's I think that's the hard part here. But the expansion looks like this. You'll do 2n of them, but half of them will be 0. That's why, oops, sorry, this is not sum to infinity, but just sum to n, right? Supposedly, remember Taylor polynomials, p sub 2n should have 2n addends, right? But what is my final answer here? My final answer only has n addends, only half of the expected number of terms, right? But that happened because half of them will just have a 0 coefficient. So yeah, that's a little bit tricky. That's why I didn't want to start with this example for Taylor polynomials, but I'm running out of time. So what we'll do on Friday is to start with the basic Taylor polynomials. I have worksheet 20, a blank version, or I will upload it later. I forgot to upload it this morning, but we'll do it on Friday. All right, guys. Sorry, I cannot do an overtime today because I have a class at 11, my second lab class for Cal 2. So let's just start. Let's just stop here and let's see each other again on Friday. All right, guys. Bye, everybody.